Dear colleagues, welcome. This is the Marine Technology Society presentation on facts to consider, material selection for long-term marine applications. I have the honor to host today's session. My name is Dr. Sidney Thurston. I'm with the United States National Oceanic and Atmospheric Administration, NOAA, in Washington, D.C., where it is now 12 noon on Wednesday, July 18th. I manage several global ocean observing programs, and I also serve on the World Meteorological Organization, Intergovernmental Oceanographic Commission, Joint Collaborative Board. The WMO and the IOC are coming together to work collaboratively, and they've had established this new panel. So I'd like to first, if I could ask Josh to show us today's registration, which I am very excited about. We have participants from all over the world. You can see we have over 650 participants from all over the world, including as far east as Japan, where it's probably at least 1 a.m. there, and then all through South Asia, India, into the Middle East, Europe, South America, and North America. So you can see you're part of a very large community, and we thank you for your contributions today. Today, we are very pleased to have one of the world's leading experts in ocean technology, Dr. Venkatasan. We have been working together for over 15 years, Venkat and I, and he's very esteemed in the international community. He's chair of the Global Ocean Observing System, regional alliances. These are distributed throughout the world, and Venkat is chair of that regional alliance. He's also on the Global Ocean Observing System, known as GOOSE, steering committee. He's been with India's National Institute of Technology, NIOT, in Chennai, where he currently serves, but he's been working in ocean technology for over 37 years. He's won the very esteemed MTS Marine Materials and fellow of the National Association of Corrosion Engineers. He's won the prestigious MTS Lockheed Martin Award for outstanding service, and many, many other awards. Personally, I've been working with Venkat for over 15 years with the Data Buoy Cooperation Panel, and we also are co-program managers. NOAA and India's Ministry of Earth Sciences, we operate a mooring buoyed array across the entire Indian Ocean, and Venkat and I are co-program managers for that. And that is one of the premier US-India scientific collaborative partnerships. So I have the honor of introducing our speaker today. And with that, I would like to pass to Venkat for his presentation. Thank you all again for joining us. And just a point of protocol here, your speakers will be muted, but please submit your questions via the chat box, and Josh will read your questions for Venkat as soon as Venkat completes his presentation. So with that, I'd like to pass it to Venkat, please.
Good morning, good afternoon, and a good day for many of you. At the outset, I thank Dr. Sidney Thurston from NOAA, my good friend, for giving this introduction. I thank Marine Technology Society for giving me this opportunity to make this presentation. So I thank all of you for sparing a time from all over the world and come to listen to this talk. Today I'll be presenting on materials, which is very important, and the selection for the long-term applications. And what is the practical experience I'll be sharing with you, some of the case studies, and what need to look at it in the long-term perspective. Before that, it is my privilege to introduce you to about MTS India section, which myself and Mr. Nandakumar, we started it in way back 4 years ago. And we have established about 9 student section. We have a large number of students who work along with us. In this short span, we could have about 108 events. We have exclusively one scholarship by the name of late Vembu, who was instrumental in starting this section exclusively for Indian students. And I'm thankful to MTS for conducting this scholarship program for the last 2 years. And with this larger activities, we could adjust ourselves as one of the outstanding section in the world. And also one of our student section, SRM student section, received the best student section award last year. And it was informed earlier that I could receive MTS Lockheed Martin Award and Fellow Award. And we also have the opportunity of bringing these marine technology among the students. About 8 student scholarships are honored to them. We conduct tech search, wherein we invite various delegates from defense and research and academic institutions to come together in 2016 and 2018. In this year, we had a student-run program called TechSim, which was organized by students themselves. We also conducted a decathlon wherein maritime communication was one of the theme, where students have to demonstrate how the communication could be done. Now, recently we launched one of the very new activity called student writing competition for students as well as the young professionals, and that is already online, and the last date is 31st July. And we also conduct, along with the National Institute of Ocean Technology and student AUV competition, where the winning team is sent to San Diego to participate in the international competition. We have 2 startups, we support them. We do have a school program, and we also conduct the plastic awareness. And our members of the MTS, they have about 23 publications in our journal. What's the motivation? Basically, the Marine Materials Committee of MTS has to be revitalized. There's not much of an activity, and being a chair, I thought I will just make this presentation and request all of you to join this Marine Materials Committee and share our experience among ourselves and to others. Where do we contribute? You know very well the United Nations launched an ambitious program of sustainable development goals. There are about 17 goals. Out of that, 14th goal is very exclusive for us, that is life underwater. However, there are 9 more goals, total 10 goals where we can contribute as a materials engineer. We can involve in design, because some of the cases, in the case of environment and sustainability, and also to the society in developing standards, and many other activities can be done. So with this in mind, I'm sure that we will be able to work together and contribute in the field of marine technology, particularly on materials. This is a very interesting slide to talk about the ocean. Even though the planet is called Earth, we know very well that 70% of the Earth is covered by water, should have been called as oceanus. And these consist of various marine biomes, and about 70% of these they consist in the estuaries, mangroves, and coral reefs. And some of them up to 200 meters, they thrive on phototrophic microorganisms, and in the deep water, they thrive on organic and inorganic chemicals for energy. We know very well in hydrothermal vents also, these organisms do exist over there. So we are going to talk about such a system where it involves both physical, biological, chemical, such a complex environment. We deal with that, where these materials and these structures need to work over there. When you talk about the current scenario of resources, the energy resources are to be looked into the ocean, particularly for water. We are looking for a desalination plant. The picture, what you see is the desalination plant designed by our institute, and we have 3 such plants working on a low temperature thermal distillation process in our islands, and 6 more are being constructed. We also work on a green energy, there is ocean thermal energy conversion plant. In future, this could be an opportunity, again leading to SDG goals. We have to look for this alternate source of energy. Yes, in defense as well as in the case of shipping, there's a larger requirement of materials to be studied and material production. And in the case of ships, we need to look for a cleaner hulls. So any ship owner would like to postpone his dry docking and have a longer longevity of these ships. So there look for a proper paint system so that that can be protected. The oil wells are going deeper and deeper. As you go deeper and deeper, there is a more requirement to look into this materials. Further, we also know that floating wind is one of the promising area. Next to 5 years, about $30 billion worth of contracts are to be signed. Already a few of them are in the pipeline where the major industries are involved. All these efforts call for a newer technology. These newer technology would have a requirement of behavior of materials and also the development of newer material for satisfying such requirements. When you talk about environment, it's subjected to chemical, biological, and physical deterioration. And it's very difficult to simulate these conditions in the laboratory. Many cases, the laboratory results may not be fulfilling the field. There are failures which have been reported. Case studies have really shown that very difficult to simulate. But broader area could be done in the lab studies. And the selection of materials involves a design and this protection for long-term applications. In the case of materials, even though newer materials have come, the metals, particularly steel, still play a major role. The high yield strength HY80 alloy steel, and the HY100, HY130, these are all commonly used for submersible studies, where the metallurgical factors played a major role in development and involving this microstructure, that strength could be increased. Of course, composites and polymers, they do play a major role. In the case of metals, again, titanium, which is widely used, but again, it's expensive and it has got a very good property of strength to weight ratio that is really useful for manned submersible and such activities. Inorganic materials, concrete, yes, is widely used for offshore structures. In the case of design, materials engineers, we know very well that the control of strength and control of toughness is possible by varying the alloy conditions, and the newer alloy could be formed and that could be developed. In the case of fatigue, where a cyclic loading is involved, the fracture mechanical phenomena is predominant there, where the geometry and the loading condition is important, and very little role is played by the alloy steels. Corrosion, which we all know, it's a chemical or electrochemical phenomena involving anodes and cathode in a particular electrolyte. It's a very simple way to define it. In the case of seawater, the electrolyte is available everywhere. The cathode and anode could be on the same substrata. For example, in the steel itself, there could be a differential aeration involving these anodes and cathodes, leading one anode getting corroded over there. So the deterioration is very common. This is what is a balance of Mother Nature, we call it, where the metals were from the mine, from the ore, the metals have been brought into the condition we call as Gibbs free energy, and human intervention is involved to bringing this. However, they try to go back to the natural phenomena where they exist. That's the reason in the case of corrosion, they try to go back to the oxide and the ore stage, they try to go there. So how do we protect, how do we ensure that these three things like cathode, anode, and the electrolyte, they don't come together? This is what is the challenge we are all talking about it here. I've shown a picture of many other corrosion phenomena are there. Here, very important thing is on fatigue corrosion. In the case of marine environment, we talk about low cycle fatigue. Normally, the fatigue corrosion is well studied for aerospace industries, which involve a very high cycle fatigue. In the case of low cycle fatigue, that too in the laboratory, that too in the seawater, it's very complex. There are failures which have taken place, and I can show the picture here. Similar simple shackles are failed by having these fatigue corrosion conditions. I just touch upon on concrete. We know very well the corrosion in concrete is one of the single largest factor responsible for the deterioration. And the alkaline of the concrete, which protects the steel, we know that. However, the chlorine ions, which is predominantly present in the seawater, can depassivate the steel even in alkaline conditions. So once a rust is formed, it has got a greater volume than the steel, and it starts exerting pressure, and the concrete starts failing. So this is a complexity involved. There are various protection mechanisms involved by inhibitors or IPCC system, which need to be taken into account. So there is a need of periodical inspection. So that activity is very important before it leads to catastrophic failure. Engineer, while he designs, he look for how do you control this corrosion, how the prevention could be done, either in the power plant or an offshore industry. So all these things have a different perspective First and foremost, in design and engineering. The design aspects need to be taken into account. Certain simple design precautions, if you take it, 100% we can try to avoid or postpone it. And selection of proper material and fabrication and construction need to be done in a proper manner, where there are codes, they clearly define how they need to be executed. We need to strictly follow these codes. Then next comes, how do you protect it? The protection could be on by using paint or a coating or a lining, which could be metallic or non-metallic. And this can prevent direct or indirect contact between the metallic surface and the environment. That's what it acts like a barrier. And the environment control, this is very predominantly used in the case of where the closed loop is there in a power plant or such systems, where the inhibitors and the chemicals try to modify the corrosive characteristics of the fluid so that the corrosion is minimized or reduced. Then cathodic and anodic protection, which is used offshore very widely, and we also use it in our structures, simple anodes, but again it calls for selection of proper anodes. If, for example, zinc anode is used, if the iron content of zinc anode is more than 14 ppm, they start doing the self corrosion, that is in the couple between the iron and zinc can lead to the self corrosion of anode rather than it protecting the surface. So I mean, now there are very well established standards are there. We all know that. So selection of proper anode, either aluminum anode or zinc anode in the case of sacrificial. In the case of IPCC, proper selection methodology is there. So the corrosion monitoring and asset maintenance are very, very important in the offshore structure. This is what is the present scenario now. We have large, means many offshore structures which are installed. They have been functioning for more than 3 to 4 decades. Now, when you talk about asset management or maintenance, there is a big question mark. What is the longevity? How do we assess that? There are standards, protocols, and the codes are available, but these aspects of inspection and the corrosion monitoring is very important. In addition to these aspects, there are also choice of coating depends on the zones. Normally in the marine environment, it is divided into 5 zones like atmospheric zone, splash zone, tide zone, submerged zone, and mud and sediment line. We can see very clearly in the picture what I've shown here. In the splash zone as well as a partially submerged zone, the corrosion rate is very high. When you talk about typical coating system for offshore applications, ISO 12944 talks about, in the case of atmospheric, you have to go for a simple zinc primer followed by epoxy coating and polyurethane coating. In the case of splash and tidal zone, we have to think of a 2 or 3 epoxy. This is very, I'm talking about generic, but again it varies from the manufacturer to manufacturer. They clearly specify. In the case submerged, in addition to epoxy coating, we need to think of antifouling coating. But for all these things, surface preparation plays a major role. That's what we are all talking about, training the applicator. Even though the paint system works very well, the application, if there are errors, that can lead to the failure. So the whole system need to be looked into it in a more collective way, so that the application, the most expensive part is the paint system, that is being applied in a proper manner. There are also NACE certified painting courses are there, and applicants are being certified. They try to do a perfect job by involving these various parameters in their mind. Next, I thought I will touch upon this important aspect of biological influence or marine organisms influencing on the metal substrate. We have done a large amount of work in this area. I'm sure a few of my colleagues who have worked with me, they have contributed. I thank all of them. And when you talk about biofilm, this is the initial stage. We normally, when you look at morning when you brush your teeth, you have your toothbrush lying on a cup of water, you have a slime formation. That is what is the initial biofilm stage, wherein the carbohydrates and salts absorption stage, where it starts formulation. Once that forms, then you have a bacterium, then immobilization takes place. Then bacterial colony starts having the exopolymer production, secretion takes place. That's what this slippery surface. Once the biofilm formation is a colonization of all, then it starts from few seconds, and subsequently it proceeds into the month and so on. This is what today we are talking. Today, COVID and many other cases, this is what is talked about. I thought this is more relevant. Some of the microbes are destructive, some are non-destructive. Yes, we have understood now. So we live in a biosphere, which is ultimately what ties the major systems on the earth together. This is what microbiologists they also talk about it. This is these biospheres where we live. It could be air and water, it could be air and the earth, it could be combination of all the three. This is what is a biosphere it is called. And these three systems together, combination of this in the earth system where we live, biosphere plays a major role. So unless you understand this, yes, we are living in a biosphere. We cannot eradicate. We have to find and look for a solution in protecting these metals. This could be in the dentist, or this could be when the case of surgery takes place. Many other applications included inside our body fluids. So the biofilm formation is the first stage. Subsequently, in marine environment, depends on the larval availability, particularly in the tropical conditions like we have in India, where it is documented by one of the research institution here that there are about 1,700 species of fowlants could be there. These organisms get attached to the surface. Normally, when we walk across a beach on the rock, you find the barnacles attached to that. So this microfouling could be initial stage of 20 microns to 1,500 micron, whereas a macrofouling, which is subsequently is a plant or an animal, which can exceed from 50 to 10 centimeter thickness. This is what we are going to discuss here. This growth of macrofouling, how does it affect the material? Now, we have done a study. What we have done, we have exposed different materials in the Indian water, particularly in Chennai, where in tropical conditions, you can clearly see that there is a settlement of colonies of, we call it the bacterial counts. That's a simple way microbiologists they do it. That's, you don't need to worry about these numbers. That talks about X. Yes, there is a film formation, microorganisms live. In the case of macrofouling, where we have seen after about 150 days, there's a growth of macrofoulants over there. The important point, there could be plant and animal growth. We have seen the plant is growing when there is a sunlight falling onto the substrate, whereas when there is no sunlight, there is animal growth. So there is a sort of symbiotic effect between these two. But the interesting part is that there is a variation in different materials having different thickness of this biofoulant or the weight. In the case of copper, it is very less. Of course, in the case of titanium, it's very no more. It's more. This is to be noted, and I will also show some more data related to this. This is what I'm trying to bring down here on the practical experience by having these coupons exposed. We have published papers. I'm linking up biology into the engineering component here. Then, when you talk about S exposure, how does it vary? We think that away from the shore, far away, it may not happen over there. This is what is normally our feeling. It's not so. Sometimes the biologists they study that this larval movement takes place because of the current. In our study, we have these moved buoys which are deployed in different waters. Our biologists they have identified different species. Mostly it's called lipas. This is the bivalve which is attached to the substrate, but they grow and they continue to have these on this substrate. Now, having seen it on the surface, even far away from 3,000 kilometers from the shore, how about subsurface? Here is the data I am presenting, wherein we have a moored system which is anchored, say at 3,000 meter water depth. We have recorded up to 50 meter depth these fouling organisms over there. In this paper, what we have published, very recently we have published, Dr. Martin, my colleague, has done a very extensive work. Here, first time we have compared the oceanographic parameters and also how these animals are growing onto the surface, what type of food and what requirement they have it, and what type of oxygen level requirement for them to grow. And does it vary? It depends on the salinity. Yes. Here in India, we have east and west coast. East coast of our country is called, we call it Bay of Bengal, and west coast is Arabian Sea. In the east coast, a large amount of freshwater influx. There's one of the largest next to Amazon. These freshwater influx leading to the lower salinity. Normally, the salinity could be 32, 33. It's less than the 28. In that conditions, we found less amount of these settlement of biofoulants. So they are not able to withstand the shock, they fall. Whereas in the west coast, where the salinity doesn't fall, we have the large amount of growth over there. In addition to that, when you talk about subsurface, we have seen in different locations when there is a freshwater flow along the coast, which is another oceanographic discussion I'm not bringing into that. Again, that is also playing a major role by having different growth rate and settlement onto the substrate. So this is to be noted as we talk about different installations of offshore structures as we try to go deeper and deeper for exploration and exploitation for long-term application. One has to look into this aspect, how these animals are growing or where it is growing, so that there is a site-specific data sets are required. That will really help you to design your system, to take a precaution in the design stage itself. This is a picture which I got it from the cruise of Neil Armstrong when they retrieved one of the synthetic foam which was deployed at 17-meter water depth from Woods Hole Oceanographic Institute, completely covered with one of the biofoulant called Dosima fascicularis. When I read about that, these particular foulant, they produce foam-like structure, like styrofoam. They produce a foam-like structure when they secrete it. From the larval to the settlement stage, this foam-like structure makes it to be slightly floating condition. This is only one of its foulant which can have this foam-like secretion from its body during the attachment stage. So they grow it and they cover the complete surface. That increases the load and damages the system which we have deployed for some other application. Basically here it was deployed for oceanographic measurement. Then what are the factors when you talk about offshore structure? Offshore structures could be broadly defined. Maybe you have a pipeline running on the seabed, when the structures could be steel jacket structure, concrete gravity structure, or tethered buoyant structure or semi-submerged structures. In the deeper water, you have semi-submerged structure. This is what the ocean engineer he studies about the structures. And how do you design it? You take into load of a wind and wave. In the case of wave, we take the significant wave height. 50 years data sets are used for calculation, and also the wave and current aspects into that, and the slashing effect of wave. There could be water shedding. There is a long discussion. There are a lot of work done in the descent stage. How this water shedding, which can give a very large load, could be avoided. And also the roughness of the surface, mainly due to the marine organism settlement, is taken into account. But I will show you that presently what they have taken into account is very small. It should be in the large level. Recently there was a seminar arranged by World Oceanographic Council wherein there was a presentation. This offshore structure in the North Sea, they have given it on leasing for removal of various bivalves and these marine organisms for commercial purpose. Some agency have collected and sold it. That amount of growth is taking place on long-term application. Then there is an array effect which is taken into account. So these are all the various aspects. And the simple, I'm not going to talk much about it. These are the simple Morris equation which is used for hydrodynamic force calculation. The force could be drag or inertial force. In the case of you have CD and CM, that has to be taken into account while doing so. When there is a marine growth, that can have an effect on the structural diameter. You would have defined a particular smooth surface. Now the diameter is changed and the force coefficient is changed, and your structural weight, overall weight, we have seen earlier picture, there is a weight of marine organism that can increase the structural weight, and the mass and hydrodynamic added mass, and also the flow instability and the members outer surface and the physical construction. These are all various factors. By having this growth can affect your original design, what you have intended, what you expected in life. So this also need to be taken into account and to be studied while designing it. Another, I'm going to show you a recently Indian coast we faced on 20th May, a major super cyclone. A cyclone is nothing but hurricane, you call it in other part of the world. This cyclone is tropical cyclone, started moving along the from the middle of the ocean and towards the coast. We have a very large settlement. I'm glad to say that Indian government and Indian Meteorology Department could give a proper forewarning, including our Ministry of Earth Sciences. And we have these observatories deployed at sea, provided information, and we could evacuate people in a perfect time. So this is what is the science is talking about, saving the lives of the people. But here I would like to emphasize here, as a materials engineer, these installations of moorings, you can see near the ship, a floating buoy anchored at 4,000-meter water depth, they need to withstand these structural loads. And when the cyclone passes through that, they need to provide data. For example, in this particular case, the wind speed was 200 kilometers per hour, and the significant wave height increased up to 7 meters. And also the various current has increased a lot. So in all these conditions, the selection of material plays a major role. Normally, a mooring is designed, in our case, we have a tension meter for less than a ton. But when this is such extreme conditions are there, the selection of these ropes and hardwares, as well as the main structure of the body of the buoy system, have to withstand these conditions. So similarly, the offshore structure which have been installed there need to withstand this extreme condition. So the designers need to take care on material selection, these extreme conditions which can lead to the fatigue loading, which is fatigue loading is very difficult to predict. So that has to be taken into account. We have seen in the earlier slide on the normal condition, but these are all the extreme weather condition that can come at any time. And this is what is a marine environment, we talk about it, very difficult to predict. You have all these things are collectively acting. You have wind, wave, current, sunlight, marine growth, corrosion. How do you define it? How do you simulate in the laboratory condition? Which modeling can work? It's very difficult. These are all the practical knowledge. Many of the technicians and engineers, they have it. That practical knowledge is helping us to design the structure for long-term application. Today we are talking about designing mining systems which need to take the minerals like manganese, nodule in deep waters. So we need to look at this aspect when you talk about long-term installation of these systems at sea. Then we also work on reliability. Reliability is nothing but how far the systems can work. What are the failures could be there from the past record you can involve your design. So we call it as reliability, availability, maintainability, and safety studies. We call RAMs. So we have published about 8 papers relevant to our system. This is available in Marine Technology Society. We also use a software called Arcaflex. We have got our own software tool in designing these mooring systems. And this is what one can clearly say, that having a practical knowledge, we use our own data and also try to check whether the system has performed very well, and we try to go back and compare the case studies. That helps us in go for improvisation. We also got a tsunami early warning buoy systems deployed at sea, which are very critical and need to function properly. So this design and selection are very, very important. Now, I thought I'll touch upon buoyancy material. There are different type of buoyancy material. In shallow waters, people use a PVC floats or polyurethane floats. In deeper water application, glass sphere was widely used. Some of the US firms, they have designed Woodstoll Oceanographic Institute. They are the premier, and when the glass floats started commercially used for various oceanographic applications as a buoyancy module. This will help you to bring back from the seabed to the surface as a positive buoyant material. And the borosilicate material is used. It has got an immense strength to weight ratio, and it's got a very high compressive strength. It also has got a transparency. So some of the underwater cameras could be fitted onto these glass floats. But next stage, they were to look for an alternate material which is also lightweight and it can occupy less space. Synthetic foam came into the picture, which is nothing but a small microspheres embedded onto a resin. These hollow spheres, fillers, can have a porosity and very high compressive strength is possible. The man-submersible, remotely operable vehicle, many of them use synthetic foam, and it has got a cover with a polyethylene or fiber reinforced plastic. Next stage, in the case of like Mariana Trench, where in 11,000 meter, where the pressure is 1100 bar, they have to look for an alternate material. So the ceramic material, silicon nitride, was devised as a material which was tested as a hollow sphere, and they have been effectively used for such applications. Here is a case, I am showing it here, where implosion of the glass floats has been reported in many conditions. I'm showing you on the right top panel where it was recorded in one of the case where you can see the explosion noise. After one single explosion, multiple explosions were recorded. These hydroforms were fitted onto a submarine cable, and close to that these moorings are there, and they could record and clearly show that this much amount of large amount of sound waves can produce. Once the sound wave starts traveling, it can have a larger impact and many other floors could damage. In our case, we have found this implosion of these glass floors. This is what a designer should understand when he designs a system. Additional buoyancy should be used in case such failure takes place. For example, we have a submerged systems which are deployed at 4 km and 5 km depth. If this glass explosion happens, the system cannot pop up over there. So the designers need to understand. And where do you find? You don't find in any textbook. You can't do it in the laboratory condition. It happens. It happens mainly due to the handling, or sometimes we do repeatedly. We don't know why. But these are all the evidences we need to share with among ourselves, wherein for marine application, we need to take care of this implosion of the glass floors. Next is on the as a materials engineer, what type of energy source when you have an ocean observation system like us, you have it. So we use solar powered system with the lead acid battery with a proper charge controller. We also use a primary lithium battery, and there is a possibility of automatic power changeover in case solar panel doesn't work. The primary lithium battery can take over. This is our own design. We have applied for a patent, so this anybody can work on it, having a redundancy when you deploy such systems at sea. It's not like an offshore platform where there's a large amount of energy source available. There are these smaller buoy systems when you deploy, we need a power requirement. There are also fuel cells which have been tried, particularly when you want to do for offshore wind studies or LIDAR measurements. We need a large amount of power source where the fuel cells are being used. So when you talk about energy density, if you look at it way back in the initial stage of 1899, now we are talking about after say 200 years, the invention of the battery. Michael Faraday played a major role. Today we have a lithium battery, but when you use a lithium battery, one has to be very careful. Yes, it gives a very large energy density, maybe up to 790 watt hour per kg. That's what we are using it. But individual cells need to be designed, particularly for primary cells. So there are systems available which we have documented it and we use it. And we also use these battery systems have got PTC fuse and diode and thermal protection. This is very, very important. Many of the aircraft, they use this lithium battery. But in the case of marine application, we need to be careful. Lithium, when it's exposed to the seawater, it can produce acid like hydrochloric acid and sulfuric acid. That can be highly corrosive. So we need to ensure that they don't come into contact with seawater. In the case of buoy system, we use safety valve, pressure relief valve, and we have a nitrogen flushing. We ensure that these gases do not accumulate. In the case of lead acid battery, hydrogen accumulation could be a chance. There was an accident which had happened earlier. So we wanted to be very cautious, and this is what many of these buoy operators, they tend to have these safety measures. Anybody else using the system, I would strongly advise to have such safety valve system. When you leave unattended floating systems at surface, there could be excretion of birds. That's what happened in that case. The bird's excretion can lead to a very high pH material that can corrode this material. And when we go there, that could be water ingression leading to hydrogen gas formation in case of lead acid. In case of lithium, there could be sulfuric or hydrochloric acid. So the safety valve is one measure which can release this gas formation inside. Then what about deep sea? Now we talked about deep sea where there are exploration, exploitation, there are activities which are started on mining. When you talk about all this system, what is our experience? So we have done a testing long ago, and there are only few publications available on different material, how they behave in underwater from surface to the deep sea. So we have tried with metals and alloys and composites up to 5,100 meter water depth, more than about 174 days. They were exposed. We have done a systematic studies in the microscope and scanning electron microscope. In the case of composites like carbon fiber composite, predominantly the results were very good. There's not much of a damage to the fiber, and the material withstood that. So this is to say, we know very well like material like aluminum 2014, which is the aerospace material, should not be used. That is corroded. We know uncoated cast iron or iron steel, corrodes. All these things are known to us, but titanium doesn't corrode is known to us. But what is the practical way? Here is a particular case where one of the bottom lander, when it was deployed, accidentally they lost it. After some time, after 3 years, the deep sea lander was retrieved. There is a growth of colonization of hydroids. This is to show that even at this depth level, there is a settlement of organisms. So, but did not have much on deterioration of the material. This is to show that there is still in this depth level where there's not much of sunlight, animal do exist over there. We know very well in hydrothermal vents also, using sulfur as an energy source, these animals can live. There are reports of crabs and many other shrimps and things like that. Here is a case where the material exposed. So we will say that yes, the previous slide and this slide, one can conclude and say that this is what many of the designers thought, that deep sea, nothing happens, we just leave it, there's no less amount of oxygen, and when there is a low oxygen level, there is not much of corrosion, there's not much of a growth of animals because in deep water. But here is a classic case wherein I'm going to talk about Titanic shipwreck. We know very well this Titanic ship which had sailed out from Southampton and had sailed through on the fateful day. It had hit iceberg. It was only a 40 seconds duration. This about 300,000 tons of ship had to sunk, and nearly 2.5 hours, the whole ship is sunk. This we all know about happened about more than 100 years ago. And what is the lesson learned from that? So these are all many of the disasters people have studied. I'm trying to quote here from one of the results. What has been shown is that why did Titanic sink? In those days, this particular ship was made of rivets, not like a present welding. And there could be design flaws or material failures or extreme conditions or environment, not necessarily preventable, or some combination of the reasons above. There are two theories which have been postulated by the author here. One is on the multiple rivet failure by this collision. Second is on the ductile to brittle transition of steel, which the particular steel what has been used, comprising of various components, leading to at -2 degrees centigrade and deterioration of the brittleness, which could have happened on this collapse of this vessel. Other side, the similar time, there is another vessel was built by the same yard and the similar specification, similar steel, that is the Olympic. The Olympic survived. Even the Titanic could have survived for 20 years had it not been collided with an iceberg. That's the big difference between these two vessels. So that played a major role of this 40 seconds activity leading to sinking of such a large vessel. Now, what happened to that? This is a current scenario. After 100 years, the research have gone and studied what is the current status of this Titanic shipwreck. Sorry, they've taken sample. I'm in touch with the researcher there, Dr. Henrietta Mann from Canada. She has done extensive studies, and it has been reported that maybe a few years down the line, 3-4 decades, this Titanic shipwreck could be completely eaten away by the microbes. You'll be surprised to know that there are vesicles, there are different species. She calls it the Christmas tree, that is lepidocrasites. These iron-reducing bacteria, we call it, and they start consuming this iron which is present over there. This is for engineers to note that, yes, we also have the present scenario. We are locked down by COVID-19 by microorganisms. Even at deep waters, where this Titanic shipwreck is, microorganisms can play a major role. The challenge for Dr. Handita Mann is to the conventional system of culturing these microbes are different. She found a new methodology and she had informed us how this was done. Why did we approach? I'm going to show in the next slide. Here is a classic case in Bay of Bengal at 3,300 meter water depth. We have deployed a tsunami early warning system, which was lying on the seabed. This particular component is about 2 meter height, having syntactic foam and 17.4 pH stainless steel, one of the highest corrosion resistant steel, and aluminum 6064 T6 alloy. And when they retrieved it after 18 months, They found a mucus substance and it was also smelling badly. I'm glad to my colleagues. Normally, they know that I'm interested in this type of activity. Normally, when you are at sea, when you do a very hard work in the day, late night, you try to clean your system and pack it and look for next activity next day. But herein, thanks to those engineers, their presence of mind, they brought this system, why these material have corroded, what type of settlement have taken place. Then we started contacting researchers, particularly microbiologists and biologists. What is this opaque substance? What is this mucus or gel-like substance, odorless material which were initially formed and later on it was having swelling? When you talk about, when we have seen the stainless steel rods, the threaded rods, which are all corroded. And we have extensively studied, we thought that it could be ambiguous from the whale. Then the whale doesn't go more than 800-meter water depth it's reported, because that could be one substance. There could be a hydrothermal vent where these bacterial colonies could be settled over there. These are all questions we approached various researchers in many countries, and we had sent these samples to them, and we have published this paper in Marine Technology Society. In conclusion, yes, it is mainly by the microbiological activity which has led to deterioration. We need to be very careful in exposing unpainted, uncoated material. This is what is support we are giving. Wherever the surface of this equipment is painted, had a coating, did not have any of this effect. Where this bare material was exposed, that led to this severe corrosion of this material. When you talk about now currently, I'm also part of a committee. We are talking about smart cable system, wherein we know that telecommunications are run more than about 1 million kilometer long telecommunication is lying on the seabed, by which we are able to operate our mobile. We are talking about, can we attach instrument to that? When we attach instrument, they have to work for 20-25 years. That's the life of this cable, which are all billion-dollar projects. But when we design a system, those cables are well protected. However, when you design an instrument, these results, one need to be very cautious and ensure that these unpainted or uncoated metal surface should not be used. There could be such failure can happen. This is also another case where SS316 material was used in this. Again, somebody thought 316 is very good, no need to paint. But it can lead to pitting corrosion, because the chlorine ion in seawater and having a biofouling on the surface can have a detrimental effect. This pinhole leading to the water ingression, and the complete system was filled with water, and the electronics inside got deteriorated. And when you talk about marine biofouling, earlier we have seen the effect of copper. Yes, we have seen these are all the conductivity temperature sensor. They have initially having a titanium guards, having severe fouling. Later on, we have replaced with the cupronickel guard or copper guard. In fact, 90% copper. That has led to reduction and also not much of fouling. Here is a case when Mr. Mark had immediately, once the announcement took place, is our MTS member, consultant of NOAA. He informed me that I should present this particular slide, wherein this is deposited in the OBS, where we ocean best practice, wherein the data well they have studied different material, and the copper has not seen fouling compared to 6 different material with a different coating. So that is a report. I thought I'll present it from the OBS. Next is on connectors. There was a talk arranged by MTS. I know some of you would have attended. It took many years for somebody to design a connector. But when you choose a material for connector material, the body of the material could be chloroprene rubber or low carbon neoprene or molded neoprene or polyurethane epoxy or a neoprene rubber. And the bulkhead could be of the body could be used either brass or stainless steel or a titanium or anodized aluminum or a peat material. So this is the heart of the whole system. When you have an underwater system, if these connectors fail, the whole system failure. So it takes place, and you also lose the data. We also lose the system, whole system collapsing of taking place. So material performance is very important, particularly when you use it for such application. Here again, I'm showing a practical case in a particular location in Arabian Sea in Northern Bay. Before that, we have documented in last 20 years, we have been using different type of connectors made of either neoprene or chloroprene. and we found more failure of neoprene compared to chloroprene. Maybe others would have similar such data. Herein, these bivalves are I've shown earlier, the barnacle growth to take place. However, like you have a borer, we also know that at home, somebody says wood borer has destroyed my wood at home. Similar to that, there is a sponge borer which is sat over on this connected, and that has diluted the connected material, leading to the copper pin getting exposed to the seawater and short circuiting it. This we find only few occasions and in a particular location, not in many places. I'm just trying to report this type of extreme conditions somebody would have faced, but it's better to note that these failure do take place in having these long-term exposure of these materials at sea. We have done a good amount of work and published on polymers degradation. Somebody would think that metals only corrode and there's not much of a degradability of polymer. It's not so. The ASTM and ISO define degradable plastic are those which undergo significant change. So with another institute, Indian Institute of Technology, with Dr. Mukesh Rople, with a microbiologist, we have published quite a good amount of work on different type of biodegradation of plastic, either bacteria, fungi, or algae. We have published a book also. So the plastic degradation and the plastic corrosion is also talked about it. That also need to take into account while designing it. What measures we take? We, in our conditions where we have mold applications, we have a proper hot dip galvanizing. We also use a customized sacrificial anodes and try to avoid metal to metal direct contact, and also alternate material wherever is possible we used. We use a fiberglass material. I'm glad to say that the main buoy system comprising of fiberglass, fiber reinforced plastic performed very well in the last 20 years. And there is a cost reduction compared to ionomer foam, which are widely used globally. These are all nearly 1/3 of the cost, and they have performed very well. Even we have designed, and we have also done the model studies in the wave plume tank, and they have also worked very well in a way for wave following conditions. I would strongly recommend. Basically, we have got a 7-layer of mat, woven mat. If somebody is interested, I can share with that, with isopropyl as a resin. So that has really made us to design such a buoy system inside having foam filled with that. That is giving a proper buoyancy system. It's weighing about 1.25 ton, and that buoy system is widely used by us. And what are the recommended anti-fouling measures? This is widely used by many of such buoy operators. You have somebody designed about anti-fouling wipers for sensors, particularly optical sensor, and copper tape, and plastic anti-fouling, and copper alloy sensor guard, which I mentioned earlier, and the clear tape, and many other things. These are all the small measures. Even in another MTS talk, this question was raised by somebody from Australia. These are all different measures which we undertake, and case-to-case basis, we have been seeing proper data collection having this. Just before concluding, I thought I will share with you on our experience on our work on biomimetics. Nature knows the best. With millions of years, they have been working and they have improvised. The nature has developed this technology of its own, and there is an excellent amount of source of innovation is possible. So our ancients have looked into the nature as a way of development of materials and devices. Sorry. Oh, the system is hanging. Here one can see, sorry, where I wanted to see the lotus effect. We are looking for a paint system for anti-fouling property, having a lotus effect, how the nature makes the water repellent. So the silicon or fluorine-based paint system are very good for anti-fouling property. So, but there is a challenge here. One side it has to be hydrophobic, another side it has to be hydrophilic because it has to touch onto the substrate. But there are anti-fouling paints working very well on underwater. But when we have a system anchored, for example, when a ship is anchored for a longer period, like in tropical waters, the foulants can get attached to that. How do we design? How do we take a clue from this nature to look for anti-fouling paint? That's one part. Here with another group of my friends, Dr. Mukesh and Dr. Ravi Kumar, we have done a very interesting study on bioadhesion. We know very well the animals are able to adhere onto the surface of a substrate. As an engineer, we are not able to make any substrate with adhesion in a wet condition. For example, painting has to be done in the dry dock and when the surface is completely dry. But how these different animals are able to adhere to the surface, what makes it happens. So metallurgists and biologists and microbiologists have joined together and we have undertaken these studies where it involved culturing of these barnacle larvae and different materials substrate. There was a PhD scholar who was settled down in US. She has done a wonderful work on characterization of these adhesive proteins and adhesion mechanism. That's very interesting. I will show you in the next slide on the mechanical characterization. By showing this, we also had another sample collected off Andaman, wherein we had a marine sponge. Some of the biologists, they know marine glass sponge. The marine glass sponge is something similar to glass. How the nature is able to produce a glass, we know very well. To have a glass to form, we need high temperature and a blow, and the silicate substrate is required, it has to be blown. But in the nature, how they are able to make. We also tried with the same, these professors, we have tested the physical properties of this glass sponge. Coming back to this work involved interdisciplinary exercise where biotechnology and material science, they work together. Herein, the cementing mechanism, when the larvae is coming on, attaching onto the surface, it starts secreting this. When the secretion takes place, something similar to when you cut a bark of a tree, we have a ring. People talk about the ring, number of rings to talk about what's the age. Similar like that, there's a secretion on this ring that only from the base plate lead to the adhesion onto the surface. When you look at the schematic illustration of this is a cross section. And some of these secretion are acidic that can corrode the material where it is found. These barnacle, when they are attached to the surface, they are very soft as long as they are underwater. They are basically a lime-based system. When they exposed, when they bring out the system from the water and exposed to the dry sun, next day we won't be able to remove it. It has to be chiseled out. So there is a strong, very strong adhesion mechanism which makes it this to happen. So in this work we have done, and also we found they have the ability to understand on different substrate, whether we have done PMMA, there's acrylic material, or titanium material, or stainless steel material. Then the settlement had differed a lot. Then what we found in a few papers we published could be the surface roughness, which would play a major role, or animals are able to understand what substrate they are adhering to that. So there is also a changes, but there are few more publications recently I've seen. But these are all the engineers can look into that in different perspective. I'm sure that in the long run, these are all the solutions can come from the nature to try to have simulate this in the laboratory conditions. With this, I'm trying to conclude here. We have not understood the Earth system very well. As a materials engineer, we need to look at ocean as a harsh environment, and any system what you deploy is very expensive. The selection of the material for various technological application is more site specific, and as a designer, you would like to optimize the selection is optimized investment and operational cost and the life cycle circuit LCC they call it, and is minimized while providing acceptable safety and reliability. This is what a materials engineer or a designer would like to select a material for a proper application. With this, I conclude. Thanks to all of you for attending this virtual seminar. Thanks to MTS for giving this opportunity. Thanks to my colleagues who helped me in organizing this, Senthil Thiru and Ramsundar and many more researchers, many more who have contributed. I'm not naming few of them who have settled down abroad. They are all good researchers. So this is what is a multidisciplinary activity I've made it a success. Finally, the main motto or the purpose of this particular virtual seminar to involve all of you in the MTS Marine Materials Committee to share our experience and I'm sure that some of you would come forward to give similar such talks. You will have vast experience than me, and that will be very grateful to this community, particularly for the new students to take over this as a challenging topic, to come forward and develop this material, contribute to the society, and contribute to the design, contribute to the structures and the marine technology as a whole. Thank you, one and all. Thank you very much.
Thank you very much, Dr. Venkatasan. Thank you very much for your expertise. I've been in this business for 25 years. I know no one with more expertise and knowledge than you. Your depth and breadth is very impressive. So thank you for your very outstanding presentation. We are coming up on top of the hour. So I would pass to Josh at the Marine Technology Society to see if we have a few minutes for questions and answers.
Yes, thank you for so much, Dr. Thurston and Dr. Venkatasan. First of all, I want to remind folks that for future webinars, you can find all of our upcoming webinars, and there's usually one a week over the next several months, at mtsociety/events, mtsociety/events. I think we have time for just maybe one or two questions. Dr. Venkatasan, the first question, do submarines require the same materials of that of marine ships, or are they different needs?
Yeah, submarines, as I told you earlier, they use a high yield strength material, HY80, HY100. These are all the material used for submarine applications.
Next question, why do certain microorganisms have an affinity to bind to different materials?
Yeah, this is what is $1 million question. We have been studying about it. Whether they're able to understand what substrate, it's not so, it may not be. The main thing is that here we talk about is the surface roughness. And that could be one of the criteria for different organisms getting attached to that. But in the case of copper, I forgot to mention about cuprous ions. The cuprous oxide which forms on the surface, that could be an effect which is not allowing the settlement to take place because they are poisonous. It's not the case on inert material like titanium or stainless steel. The surface itself is inert, so the settlement can take place unabated. In the case of steel, the material itself is corroding and falling a lot. When the iron oxide is falling, along with this fall and also can fall.
Our next question, for ocean surveillance, have you found a better use for fibers as opposed to metallic or plastic structures?
Yeah, the ocean surveillance, yes, we have also used for the, as I told you earlier, the fiberglass is one of the material which should be used. But one need to be cautious when you talk about a large structure. We are talking about whole unit as a buoy system, they work very well. But as a structure, like offshore structure, when you talk about it, one need to be very cautious. Still, steel is preferred, mainly because for the ability to work at sea, and also to repair, and also the way how we handle steel. But again, protection of the steel by having a proper coating system, that is what is widely being used. I'm sure that the days to come, we also tried with the carbon fiber composite. Yes, that's also an alternate material, but again, it's expensive. That's what is called about it.
Okay, and our final question for today. There are many paints that are used on ships for extending the life of the hull. What is the procedure adopted to ensure that these paints do not impair the environment due to chemicals that are present in them?
Yeah, it's a very interesting question. Since I associated with the International Maritime Organization, I was also part of a committee wherein we have devised on how this, you know very well, by 2018, there is earlier to that, there is a proper antifoulant was used. This antifoulant having a detrimental effect on non-targeted species. And those chemicals have been removed. Subsequently, as I said earlier, the large amount of research leading to antifoulant comprising of either or silicon-based or fluorine-based paint systems have been used. They are all not having any effect on the system. That's the reason there's a more emphasis on having a proper paint system. This is what is a paint manufacturers, they talk about it. Even there is a when your ship is taken for a dry dock, you know, a large hull of a vessel, there's a proper procedure which IMO was laid down. This paint system which has been scrapped should be properly disposed of. These are all well taken care. Even a cleaning of the surface, even at the port, many other things are taken care. IMO guidelines could be referred for further such things.
Well, on behalf of MTS, I'd like to thank both Dr. Venkatasan and Dr. Thurston for attending today, and all of the folks from all around the world who took part. We invite you to come back next week and the week after that, the week after that. And again, our greatest thanks to you, and we hope to have you back here once again. Thank you so much, everyone. This concludes the webinar.
Thanks to Dr. Sidney Thurston, thanks to Josh and all other attendees. Thank you, one and all. Thank you very much.
Thank you very much.